The sun has been exceptionally dynamic of late, and it's going to go through a basic and interesting change: the inversion of its magnetic field. This peculiarity happens generally at regular intervals, denoting the midpoint of the solar cycle, and it has extensive ramifications for us here on Earth. Truth be told, it's conceivable that quickly the sun could represent a serious gamble that could bring about complete mayhem and disaster for everybody in the world. As you're going to find, the sun's magnetic field is created by the development of electrically charged gases in its interior, a cycle known as the solar dynamo. Over the long haul, this magnetic field turns out to be progressively intricate and contorted because of the sun's revolution and convective movements. In the end, this process leads to a total inversion of the magnetic polarity. The north magnetic pole turns into the south magnetic pole and vice versa. So how about we break down the entire process and take a closer look at the sun? The sun is made fundamentally out of hydrogen and helium as plasma, a state of matter where electrons are not bound to atoms, resulting in a combination of free electrons and ions. The sun's interior is divided into several layers, with the core at the center encircled by the radiative zone and the convective zone. The core is the sun's deepest area, where nuclear fusion occurs, converting hydrogen into helium and producing tremendous amounts of energy. Above the core lies the radiative zone, where energy is moved outward through radiation. In this area, energy moves slowly outward as photons are repeatedly absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is moved by convection. Hot plasma rises towards the surface, cools, and then sinks down, creating convective flows. The solar dynamo process works primarily in the convective zone and the T-line, a thin layer that lies between the radiative zone and the convective zone. The T-line is significant because it's where the sun's differential rotation and shear flows play a crucial role in generating the magnetic field. Now, here's something fascinating that you probably won't have heard. The sun doesn't rotate as a solid body. Rather, various parts of the sun rotate at different rates, with the equator spinning faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the magnetic field lines, intensifying the magnetic field. The solar cycle is an approximately 11-year cycle during which the sun's magnetic field goes through a series of changes, culminating in an inversion of its polarity. This cycle is driven by the solar dynamo and includes several phases. At the start of the solar cycle, the sun is in a state of solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is generally simple and bipolar, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the emergence of magnetic flux from the sun's interior. These sunspots appear in pairs with opposite magnetic polarity and migrate towards the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes extremely complex and tangled due to the constant twisting and shearing by differential rotation and convection. As solar maximum wanes, the magnetic field begins to reorganize itself. The twisted and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity. The north magnetic pole becomes the south magnetic pole and vice versa. This process is facilitated by the movement and reorganization of magnetic flux regions. After the polarity inversion, the sun enters a period of declining activity, returning to solar minimum once again. The magnetic field simplifies, and the cycle is ready to start anew. Currently, we're in the solar maximum stage, and the sun's magnetic field is about to flip. During this stage, we can expect to see some spectacular activity from the sun that could be as dangerous as it is fascinating. However, the sun's magnetic field inversion is not an abrupt flip but rather a gradual process. As the solar cycle progresses, the sun's magnetic field undergoes a series of changes. When the magnetic field is at its most twisted and tangled state, it reaches a tipping point and begins to reorganize itself, resulting in a flip. So do we have any idea when the sun's magnetic field is going to reverse? Researchers monitor the sun's magnetic activity using a variety of instruments and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the Sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the Sun's magnetic field and its changes over time. One key indicator of an impending magnetic inversion is the behavior of sunspots during solar maximum. Sunspots appear more frequently and are more pronounced as they move towards the Sun's equator, signaling that the magnetic field is becoming more unstable and is preparing to flip. While we're on the subject, let's delve a bit deeper into sunspots. When the Sun's magnetic field lines become twisted and tangled due to differential rotation, the Sun's equator rotates faster than its poles, causing the magnetic lines to stretch and twist. When these lines circle over the Sun's surface, they inhibit the convective flow of hot plasma from the Sun's interior. This results in the cooler, darker patches seen in sunspot images. Sunspots are not just intriguing solar features. They can sometimes produce very powerful solar flares and coronal mass ejections, CMEs. These phenomena release enormous amounts of energy and charged particles into space. When directed towards Earth, they can disrupt satellite communications, affect power grids, and pose risks to astronauts in space. Moreover, increased solar activity can enhance auroras, but also raise radiation levels in Earth's upper atmosphere. So while we're on the topic, let's explore the difference between solar flares and coronal mass ejections. While both are intense eruptions of energy from the Sun, they differ significantly. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit a lot of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as a flash of bright light and heat on the Sun's surface, like a massive explosion. In contrast, CMEs are massive releases of solar wind and magnetic fields from the solar corona. They can be thought of as giant bubbles of gas and magnetic fields hurled into space. When a coronal mass ejection occurs, it sends billions of tons of solar particles into space at extremely high speeds. So while solar flares and CMEs are related, they are not the same. A solar flare can occur independently, but sometimes a particularly powerful solar flare can be accompanied by a CME. While a solar flare does not necessarily cause a CME, they can be associated. In terms of hazard, it depends on what we're discussing. Solar flares can disrupt radio communications, navigation signals, and pose a significant risk to astronauts in space due to the intense radiation. CMEs, however, can have a more widespread impact. They can cause geomagnetic storms that disrupt power systems, satellite operations, and those beautiful auroras. They can also increase radiation in Earth's atmosphere. While solar flares are intense and potentially harmful, CMEs tend to be more dangerous on a broader scale due to their ability to affect Earth's magnetic field and consequently pose a serious threat to Earth's technology and infrastructure. Another consideration is that during periods of high solar activity, the amount of cosmic radiation reaching Earth also increases. Satellites and other spacecraft are particularly vulnerable to heightened solar activity. The charged particles from the Sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. However, apart from causing damage to technology and infrastructure, what else can happen to the planet? While the Sun's magnetic field inversion does not directly affect Earth's climate, the related changes in solar activity can have an impact. Some studies suggest that variations in solar radiation can influence atmospheric conditions and climate patterns. For example, increased solar activity can lead to a slight warming of Earth's atmosphere, which could exacerbate existing climate change trends. It could be said that auroras are probably the only positive aspect we experience here on Earth. One of the most remarkable effects of increased solar activity is the enhancement of these stunning lights. These natural light shows, known as the northern and southern lights, occur when charged particles from the Sun interact with Earth's magnetic field and atmosphere. We hear a lot about the aurora borealis, but these lights can also be seen around the South Pole. During periods of high solar activity, auroras become more frequent and can be visible at lower latitudes, providing spectacular nighttime displays. However, besides the beautiful auroras, there are more concerning aspects of the Sun's magnetic inversion that could occur if we are not prepared. Something could happen resulting in chaos worldwide. One of the most significant dangers associated with a magnetic field inversion is the increased likelihood of geomagnetic storms. These storms occur when solar wind, laden with charged particles, interacts with Earth's magnetic field. In extreme cases, they can cause widespread power outages and damage infrastructure. One such event occurred before. On the morning of September 1, 1859, astronomer Richard Carrington was observing the sun through his telescope, as he had done many times before. However, what he saw on this particular day would go down in history as the first recorded solar storm. At 11:18 a.m., Carrington observed a brilliant flash of white light emanating from a group of sunspots. This event, now known as the Carrington Event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington saw was an enormous solar flare, an intense burst of radiation resulting from the release of magnetic energy stored in the sun's atmosphere. This flare was so powerful that it released a massive coronal mass ejection, CME, directly towards Earth, traveling at an astounding speed of over 4 million miles per hour. The CME reached Earth in 17.6 hours, a remarkably short time considering the Sun is 93 million miles away from us. When the CME slammed into Earth's magnetosphere, it triggered a geomagnetic storm of unprecedented intensity. The impact was immediate and widespread, disturbing Earth's magnetic field and causing currents in the ground and in telegraph lines. Telegraph systems, which were the backbone of global communication at the time, experienced severe disruptions. Sparks flew from telegraph machines, operators received electric shocks, and some telegraph stations even caught fire. In some instances, the induced currents were so strong that telegraph operators could send and receive messages even after disconnecting the batteries. One of the most striking and memorable consequences of the Carrington Event was the spectacular display of auroras. During the Carrington Event, the auroras were so bright and widespread that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the skies illuminated with vivid colors. The auroras were so intense that they lit up the night sky to the point where people in the northeastern U.S. could read newspapers by their light. In the Rocky Mountains, gold miners were reportedly awakened by the brilliance, mistaking it for morning and starting to prepare breakfast. People described the sky as having shimmering red, green, and purple curtains of light moving and sparkling across the horizon. Now imagine if a solar storm of the magnitude of the Carrington Event were to hit Earth today. The consequences would be nothing short of catastrophic. The Sun is undergoing a fundamental change, the inversion of its magnetic field, a process that occurs roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, can have far-reaching implications for Earth, potentially causing disruption and disaster. The Sun's magnetic field is created by the movement of electrically charged gases in its interior, resulting in a complex magnetic field that eventually reverses its polarity. The Sun is primarily composed of hydrogen and helium plasma, with energy produced by nuclear fusion in the core. This energy is transported outward through the radiative zone and then by convection in the outer layers. The solar dynamo mechanism, which operates in the convective zone and the T-line, generates the Sun's magnetic field. Differential rotation of the Sun, where the equator rotates faster than the poles, stretches and amplifies magnetic field lines, driving the solar cycle. Currently, the Sun is in the solar maximum phase, where sunspots and solar activity are at their peak, leading to potential hazards such as solar flares and CMEs that can disrupt satellite communications, power grids, and pose risks to astronauts. Scientists monitor the Sun's magnetic activity and sunspot behavior to predict the timing of the magnetic field reversal. Sunspots, which result from twisted magnetic lines, can produce solar flares and CMEs, both intense bursts of energy that affect Earth in various ways. While solar flares emit radiation, CMEs release massive amounts of solar particles into space. These phenomena can enhance auroras but also present serious threats to Earth's technology and infrastructure.